Hello students, welcome to our uncle. Good evening to all.
Good evening, sir.
Good evening, sir.
Good evening, sir.
Good evening everyone. So today, first of all, we will study about reciprocal lattice. But first of all, I will be asking the very important question from you, that what is the requirement of reciprocal lattice? When you have already accessed the direct lattice and got the information regarding the crystal structure and everything, then why you are moving towards the reciprocal lattice? Everything we have done with the direct lattice, no? Then what is the need for the reciprocal lattice? Is there anything missing in the direct lattice? Yes? Anyone? Am I audible?
Yes, sir, you're
Yes,
sure.
sir.
So nobody was thinking of I thought there is
No,
not-
sir, actually, we don't know what is lacking in the direct lattice.
That's fine. That is not the problem. Now see, actually, the main reason is we are able to access large amount of information in small space if we consider the reciprocal lattice. This is the only reason that we are considering the reciprocal lattice. Now you see why. Now there is a reason. Suppose there is a set of planes like this. Like this and so on, okay? And suppose this distance is A. Then there is another set of planes like this. There is one additional between the earlier present atoms, like this. Are you able to understand this diagram? Now this spacing is A by 2. Okay?
Yes, sir.
And similarly, we can go for this one. There will be 2 in between the given one. Then what will be this distance? This will be A by 3. No? A by 3. So we have divided the available distance into 3 parts. No? Then, now you see. If this is the reference one. We have taken 3 only, no? So up to 3 only. Now, very important thing. This dot, it represents this complete set of planes. This dot, and this distance is 1 by A. And this distance will be 2 by A. This 2 represents this complete set of planes. And this 3 represents this complete set of planes. Means parallel set of planes, they reduce to 1 point when you consider reciprocal lattice. So you can see in this much space, you are having all the information that was contained in these set of parallel planes. This. Is it clear? Please tell me.
So can you please repeat 1, 2, 3? What is that?
This is one first set that we have considered with the lattice spacing A. And if the lattice spacing is A in direct lattice, then it corresponds to a spacing of 1 by A in reciprocal lattice. It means there will be a point at a distance 1 by A from a reference in the reciprocal lattice, and that point will represent this set of parallel planes. That's why I have written 1 over there. This one is corresponding to this whole set of planes. And similarly, this is second one, this is third one. Now, the distance here was A by 2. No? So just do the reciprocal of this. This will become 2 by, and similarly here, reciprocal of this. This will become 3 by, like this. Okay? So each of these points, they are representing this complete set. This is what I'm saying. Now please check.
So, sir, this point will contain the entire information of that set of parallel planes.
What is the information in that plane? Tell me. The information is that the lattice spacing is A, no?
Middle indices, probably.
Yeah, of course, you can access them from the spacing only.
Okay, sir.
So if you know the spacing, from here also you are getting the spacing, just get the reciprocal of this. If it is 1 by A, then take the reciprocal of this. It will be A in the direct
Okay, sir. Okay, I got it. Thank you.
You are getting the same information from this one dot. No? Okay? Is it clear or not?
Sir, is this like we are making this concept to understand more about this, or is it like something which is real you are talking about, like the dot, like minimizing that whole thing into locating that at this point?
Yeah, actually this is so because we are having mathematical expressions for calculating the reciprocal lattice vector. So it is not an imaginary thing. So when you can solve something mathematically, it is always real.
Okay, and this point O, it is the origin, or?
Yeah, origin. You can call the origin of the reciprocal lattice,
Okay,
or the reference one from where you are measuring the distance. Okay? Clear?
yes, sir.
Anyone else? Means this is the reciprocal lattice. Let me write. This is the reciprocal lattice corresponding to these 3 set of planes. This is real lattice. Now I think it will be more clear. This is real lattice. This is also real lattice. And corresponding to these 3 real lattice, you can see we are having a reciprocal lattice within the small space. Okay? So in a reciprocal lattice, each point corresponds to a set of planes in real space. Now, kindly read this line. Are you able to understand? This is what we have already discussed. So this is the concept you need to remember. That in reciprocal lattice, each point it corresponds to a set of planes in real space. Clear?
Yes, sir.
Yes, sir.
Now, there is a relation between reciprocal lattice vectors and direct lattice vectors. Okay. Suppose the primitive translational vectors of the direct lattice are A, B, and C, and that of reciprocal lattice are A star, B star, and C star, or you can represent them by capital ABC. Okay, then these are related by these relations: 2 pi B cross C divided by A dot B cross C, B star 2 pi C cross A, B dot C cross A, and C star 2 pi A cross B, C dot A cross B. And this is the volume, and these three quantities they are same. And this is nothing but volume of unit cell with edges A, B, and C, or the volume of the parallelepiped you have been referring to, whose adjacent sides they are represented by ABC. Okay, clear? So these are the formulae you need to remember in order to get the reciprocal lattice vectors from the direct lattice vectors. And now let us check what about the reciprocal lattice vectors of simple cubic, body centered cubic, and face centered cubic crystals. Okay, noted?
Yes, sir.
So you can write the heading reciprocal lattice for a simple cubic lattice. Now, what are the direct lattice vectors for simple cubic? Atoms are at the corners only, and each edge is equal to A. So what are the primitive translational vectors? They are A I cap, A J cap, and A K cap. Because all the edges they are equal to A. Now let us first calculate the volume of simple cubic unit cell. What is the volume? A dot B cross C magnitude. This na. So this will be A I cap dot with A J cap cross A K cap. So this will be A cube I dot J cross K. Now J cross K is what? Anyone? J cross K is I na?
Yes, sir.
And I dot I is 1. So it is nothing but A cube.
Yes, sir.
So why I have calculated this? Because this term is there in the denominator of all the reciprocal lattice vectors. A dot B cross C, B dot C cross A, and all of them they are equal. So it means I am able to solve the denominator. Now we need to solve the numerator part only in order to get the reciprocal lattice vectors. Noted everyone?
Yes, sir.
So now you can make use of these formulae, A star, B star, C star, in order to calculate. Now the reciprocal can I write volume over here because we have already calculated the volume part instead of writing the denominator term again? This way it will become easier. No? Now this will be 2 pi by A I cap. No? Please check. Again, this is V. And K cross I is what? J. No? Please check. Now what do these equations indicate? What is the information you are getting from these equations? It means all the three reciprocal lattice vectors are equal in magnitude. All are equal in magnitude. No? 2 pi by a, 2 pi by a, 2 pi by a. And what does it mean? It means that the reciprocal lattice is also simple cubic. It means reciprocal lattice to simple cubic lattice, it is also simple cubic. Please check. Clear? All the vectors, they are having magnitude 2 pi by a. And they are mutually perpendicular, just like the primitive translational vectors of direct lattice. See here. Here also they were equal in magnitude. And this is the characteristic of the simple cubic lattice. Okay. Now similarly, we can calculate the reciprocal lattice vectors for a PCC lattice. But for that, you need to know the direct lattice vectors. Now, what are the direct lattice vectors of PCC lattice? These, where A is the cube edge and ijk, you know, they are the respective unit vectors along xy and z axis. Now, what is the volume? The volume of the primitive cell.
A cube by 8.
A cube by
8.
No, it's not 8. There are other vectors also, no? ijk's. They will also contribute something. You are just multiplying a by 2, a by 2, a by 2. But each of these vectors, they are not having magnitude 1. Kindly check. It will be a by 2. Now, this will become I cross I will be 0. Of course, first of all, we can write a square by 4. I cross I is 0. Then another term I'm having I cross j. Then I cross k. Then j cross I. J cross j will be 0, so I'm not writing that term. J cross k. K cross I.
It's the answer a cube by 4.
A cube by 2.
A cube by 2.
Yes, I.
So now we can also take this a square by 4 factor outside, so it will become a cube by 8. This dot. Now, what is this? I cross j. It is k, na? I cross j. I cross k. I cross k minus j, so j cross I minus k. I k cross I j minus k cross j. I. Please check. This should be plus I. Please check, everyone. You know about cross product, na? They are in cyclic. I cross j is k, j cross k is I, k cross I is j, cyclic. If it is anti-cyclic, then there is a negative sign. Now you can see k cap and k cap will get cancelled because one is positive, other one is negative. Noted, everyone?
Yes, sir.
Yes, sir.
So volume is a cube by 8, and then it was I plus j minus k, and it will be like dot with 2 I plus 2j. So this 2 factor can be taken as common. So we are left with a cube by 4 and this dot product. So I dot I plus j dot j. The rest of them, they will be 0. I dot j, k dot I, k dot j, because they are mutually perpendicular. Please check, everyone. So now by using this, we can obtain now. Will you calculate these reciprocal lattice vectors A star, B star, C star?
Sir, A star becomes 2 pi by a. It's y plus j.
Yes, very good. This is a cube by 2, and B cross C will be now. Please take their cross product. It will be like I cross j, I cross k. I'm only writing the non-zero ones. If you are not comfortable, if you are not comfortable with kindly mute yourself. There is another way of getting the cross product, like this. 1 minus 1, 1. This way also you can calculate this cross product. So you can see you are getting 2i plus 2j. If you are not comfortable with this way, okay, so then you can calculate this cross product in this manner. Clear? Is it clear or not? Why are you unmuting unnecessarily? Please check. Use this method for finding the cross product. This is a lot easier. Please check.
Sir, I'm getting 2ik plus 2kk.
I have solved it, but you can check it from the slide. I have already solved
Okay,
it.
sir.
You can check where you have done wrong. This is minus I plus j plus k, so that's why it is minus 1 plus 1 plus 1. And in the second vector, it is 1 minus 1, 1. K
Yes,
cannot.
sir, I have put, yes, sir, I have put minus sign before the ik in the second row.
Okay, that is the mistake. No? You have done. Now, similarly, you can get B star. Now, what is the value of B star you are getting?
That's 2 pi by a. J plus k. J plus k.
jk plus kk.
Yes. So now I won't be solving this one. I will be writing directly. Okay. So this will come out to be 2 pi by a j plus k. And similarly, C star.
I plus
2 pi by a kk plus ik.
Yes. Please check everyone. Now, what is the information we are having? It means in reciprocal lattice, atoms are present within the phase centers, because this I plus j, if this is I axis, suppose this is j, then the atoms are present in the middle, like this. Suppose this is I, this is j, this is k. I plus k means the atom is present in the middle, like this, isn't it?
Yes, sir.
So means the atoms are present at the phase centers. It means the reciprocal lattice to BCC is FCC.
Yes, sir.
So these are the please check.
Yes, sir.
Reciprocal lattice for a FCC lattice. These are where A is the cube edge, because they will be present midway between the two edges. That's why A by 2 is there. Now, what is the volume?
Sir, a cube by 4.
Yes. Let us multiply these three together first of all, and then we can calculate this cross product in the similar manner as we did earlier. Now, this cross product will be given by, first vector is j plus k, so it is 0, 1, 1. Second is I plus k, so it is 1, 0, 1. So I. Zero minus 1. Again 0 minus 1. So I plus j minus k.
Yes, sir.
It will be 2. One each from I and j dot product. Please check.
Yes, sir.
Please note down. And now you can calculate A star, B star, C star, and you will see that they will come out to be identical to the primitive vectors of the BCC lattice, and hence the reciprocal lattice to FCC lattice will be BCC. A square by 4, and this dot product we have already calculated. This was like I plus j minus k. Na? So it will be 2 pi by a, I plus j minus k. Is it? Please check. This was I plus k. Na? I have written cross over there. Please check.
Yes, sir.
Now these are the primitive vectors for BCC. Na? Exactly.
Yes, sir.
Noted, everyone? Please check.
Sir.
So try to solve this question then. So first of all, you have to calculate the volume, and volume is nothing but A dot B cross C. So let us calculate B cross C first. This now. Please check. Now we can put this value over here, and then we can calculate the volume. I think I can do it here only. By 2 dot with
Sir, it is A square by 32 I plus
square by 16, not 32, because it will be A square C by 32, A square C by 32 twice. Na? Because both the dot products are contributing, na? I dot I and J dot J. Clear? Are you getting the same answer? A square C by 16?
Yes, sir.
No. Primitive vectors for the reciprocal lattice. So now we are already having the volume and this B cross C partner. So what is the answer? AC will get cancelled, and of course, in first part it will be 1 by A and 8 by A, isn't it? So it will be like 2 pi by A I cap, 16 pi by A J cap. Please check. Please check. Done, everyone?
Yes, sir.
Yes, sir.
Getting the same answer?
Yes, sir.
Another one. Now about 2D. Now, how will you find A star and B star? Because 2D means the reciprocal lattice is also going to be 2D. And it means you need to find A star and B star. But if you have a look at the formula for both A star and B star, they involve C. But C is missing. So what has to be done? Means without C, we cannot calculate these reciprocal lattice vector. So what is to be done? So in such a case, we always assume that C is equal to K cap. We always assume it to be a unit vector so that it is associated with the direction only and the magnitude is unity. Okay. So now you can calculate A and B. What is the volume first of all? What is this cross product equal to? I cross K minus J. It is 4. Na? So how much? Pi I minus pi by 2j, is it? And please check, are you getting pi j cap from here?
Yes, sir.
Yes, please, everyone check.
Yes, sir.
Now, further information regarding now, whenever we study crystal structure with the help of X-ray, okay, suppose you are studying diffraction from a lattice, then depending upon the lattice, what will be the difference in diffraction corresponding to one lattice and the other lattice? Yes, anyone? Means there are two lattices, they may be different. Suppose they are different lattices. Then according to you, what should be the difference between the diffraction pattern because of those two lattices? On what factors should that depend? Please tell me. No, I'm not asking.
So, so maybe the distance between the parallel lattice plate.
If the distance is same, then suppose the distance is same, then there will not be any difference between the diffraction pattern.
Obviously, the grazing angle.
Suppose that is also same.
So maybe on the size of the atoms.
Size of the atoms means size of the atom.
Sir, angles?
No, I'm saying angles are same. Then, of course, it depends upon the size of the atom. Very good. Someone just answered that it depends. Yeah, on intensity distribution will get affected, but how it will get affected on what factor does it depend? That's what I'm asking. The very first answer we have got is it should depend upon the type of the atom, more appropriately on the type of the atom. And what is the other factor? Structure. The very first thing is the structure. No? You people are saying that the planes or the distance, but you have forgotten the basic that if one lattice is BCC, other is FCC, then obviously it is going to be different. Okay. So it will depend upon these two factors. The structure, it means the lattice. When we are saying structure, it means lattice. And the second thing is atom. Clear or not?
Yes, sir.
So now there are quantities associated with these things. So now why I have asked this question? That is different. Why are you unmuting? Uzma. Again, you have unmuted. What are you doing?
Sir, actually, for my mistake, sorry.
Continuously, you are unmuting again and again. Or there is some problem.
Sir, actually, there is some problem in the device.
Okay, no problem, no issue. Now see, the difference between various crystal lattices is only about their structure and the atoms present within the crystals. Na? That is the only difference that we will have among any two crystal structure. That's why I have asked this question, and that is the thing that is going to affect the intensity distribution whenever we look for the X-ray diffraction pattern. Okay, so then there must be some method or the mathematical formula to access this information. Okay, please tell. Anyone? There are structure factors for this. Now, what should be the structure factors according to you? Structure factor means they depend upon the lattice. They depend upon the lattice. And intensity is proportional to, they are denoted by capital F. So intensity, it is proportional to square of the structure factor. Okay. Clear? And these f they are given by f e power iota 2 pi HKL. These are the Miller indices, and they are summed over all the gth atoms. Okay. Now this factor, it depends upon HKL according to you. It depends upon HKL only. Now what is this F4? Obviously this is corresponding to the structure. This is corresponding to the atom. This is called atomic scattering factor. This takes care of the fact that the X-rays are being scattered from which type of atom, whether it is sodium, whether it is chlorine or chloride, or whether it is copper or iron. Okay, that is being taken care of by this atomic scattering factor. Now, if the unit cell is monatomic, if only one kind of atoms are present, then this factor, it is not important to us because all the atoms are alike. Then the only thing that is important to us is the lattice, because all atoms are alike, so atoms are not important. But if the lattice is polyatomic, means more than one kind of atoms are present, then both these things, they are important. That X-ray has scattered from which position and from which atom. Then both these things, they are important for us in order to access the information. Please check if this is clear to you. There is a lattice. Let me make the lattice. And you are studying X-ray diffraction. And suppose all of them, they are sodium. All of them, they are sodium. Now, the major concern for us in this crystal will be the position from where X-ray is getting scattered. Because all the atoms are sodium, we already know that all of them, they are sodium. So we won't be asking this question that from which atom this X-ray is being scattered, because we already know this thing. The only question that can be put here is that from which position the X-ray is being scattered, isn't it?
Yes.
Examiner is going to ask you only this question from you in this kind of crystal. It is called monatomic lattice. This is the case of monatomic, and in this case, only the position is important. But if it is polyatomic, now suppose polyatomic is there. Polyatomic means at least two kind of atoms are there, or more than that. For example, sodium chloride. Then the examiner can ask you both the questions that from which position. Now suppose all the atoms, these are of one kind, and then there are the atoms present at the suppose phase center. वो भी consider कर देता हूं, so that you are able to understand easily. Now suppose two kind of atoms are present like this, blue one and red one. Okay, so now both the questions can be asked whether the X-ray is getting scattered from red one or blue one, and from which red one and which blue one, because red is this one also, this one also, this one, so they are present at a different position, and blue ones are also present at the different positions. Now clear?
Yes, sir.
Now both the questions, they become important. Clear?
Yes, sir.
Now, let us calculate the structure factors for different positions, different crystal lattices, that is simple, cubic, BCC, and FCC.
Sir, what was that intensity about?
Which intensity of the X-ray diffraction pattern? I told you yesterday also that intensity means that peak. This is intensity, height of the peak. This was 2 theta. Okay. This is the intensity, height of the X-ray diffraction peak, that is called intensity. Now, structure factors for simple cubic. Now, what are the X, Y, Z values for simple cubic? Of course, in simple cubic.
It's A, I, A, J, A, B.
No, it is 0, 0, 0. It is 0, 0, 0. So you have to put this 0, 0, 0 in the expression that we have written. H into 0, K into 0, L into 0. So it will be 0, and e raised to power 0 is 1. And you can see it is independent of HKL, which is independent of, means all the planes are equivalent. Means in simple cubic, or all reflections are present. Arun, actually, this is from the reciprocal lattice. When we have transformed this direct lattice to reciprocal lattice, we are getting a point at the position 0, 0, 0 in reciprocal lattice. That is the thing.
Okay.
Because atoms are present at the corners only, no? You can otherwise remember it. That is X, Y, Z, they are 0, 0, 0. Means atoms are present at 0, 0, 0 and the equivalent positions. If you take the reference as the corner, so then 0, 0, 0 will be the possible position of the atom. Is it?
Yes, sir.
It means in simple cubic, the HKL values, they do not matter. Means all the planes are equivalent. The diffraction, it means the diffraction peak will be from all the planes. Now structure factors. for BCC unit cell or lattice. Now, in this case, atoms are present at 0, 0, 0. Actually, in simple cubic, there was only one atom per unit cell. Na? Okay. And in BCC, how many atoms? 2. Na?
Two atoms.
So now we are
Two, sir.
considering 2 of them. In simple cubic, we consider one only at 0, 0, 0. In BCC, we are considering 2 of them at 0, 0, 0 and half of half. Okay. These are the 2 atoms. So all the corner atoms, they are represented by 0, 0, 0, and the one at the body center is being represented by half of half. Clear? Now put these values in that expression. This will be e power 0 and this will be e power pi. Now e power 0 is 1. Now it depends upon HKL. Now we know that e raised to power iota 2n pi is plus 1 and e raised to power iota 2n plus 1 pi, it is minus 1. Isn't it? Where am I?
Yes, got it.
Please check. It means it is going to be, if h plus k plus l even, it will become 1 plus 1, that is 2f, and it will be like 1 minus 1. Let me write it in this manner, equal to 2f if h plus k plus l is even, and it will be 0, means 1 minus 1, 0 if h plus k plus l is odd, because then it will contribute to minus 1, and this corresponds to missing peak. Na? If f is 0, intensity will be 0, na? It means no peak is there. It means if sum of HKL values, for example this plane 1, 0, 0, sum is odd, na? It means in BCC reflection from 1, 0, 0 is missing. Similarly from 2, 1, 0, it is missing. Okay, means you won't be able to get the peak in the diffraction pattern corresponding to these planes. You will only get the peaks in the diffraction pattern corresponding to those planes in BCC where the sum of the Miller indices is even. Clear? So I have given 2
Yes,
examples that these will be missing one. Any doubt to anyone? Okay. Now how many atoms were there per unit cell in FCC? There were 4 of them, no? And what can be their position? Obviously, one at 0, 0, 0, other one at 0, half, half. Each of the phase centers, half, 0, half, 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 0. Is it? So now you can calculate this. Now, we know that sum of 2 even numbers is always even, and sum of 2 odd numbers is also even. Okay, and we are adding 2 of them at a time, and we have already seen that if there is an even term in the power, then it corresponds to plus 1, and if there is an odd term in the power, then it corresponds to minus 1. It means if any of these sum, it becomes odd multiple, odd number, then it is going to contribute minus 1, and if it is even, then it is going to contribute plus 1. Okay. Now, if HKL are either all odd or all even, then all of these sums they will be even, because sum of any 2 odd numbers and any 2 even numbers, it is always even. Isn't it? Please check.
Okay. Last one.
But if they are mixed, if all of them they are even, suppose all of them they are even, like 2, 2, 2, then this sum will be even, this will be even, this will be even, then what will be the contribution? 1, 1, 1, and 1 is already there, then it will be 4f. Na? Please check.
Yes, sir.
And now suppose all of them they are odd. Again, the sum of 2 of them at a time, it will be even. Please check. 1 plus 1, 1 plus 1, 1 plus 1. Even then, all of them they will contribute 1, 1, 1. That's what I have written. That HKL are either all even or all odd. Then it will be 4f. Okay, and it is going to be 0 if HKL are mixed. Now mixed means either one of the index is even, 2 are odd, or 2 are even, 1 is odd. I will give you one example on the next slide. This one clear, na? All even, all odd case. Or you need more example? I have given 2 examples. All even, all odd. In both the cases, we are able to get 4f. Clear or not?
Yes, sir.
Clear, sir.
Now let us discuss the example of mixed one. Now let us suppose it is 2, 1, 1. This is mixed, na? 2 is even and 1, 1 they are odd. Now what is h plus k? 3. H plus l. 3. K plus l. 2. Now you see, one of them is even and 2 of them they are odd. So f will be, let me write, it will be e raised to power iota pi. First of them was k plus l. It is 2. Then e raised to power iota pi. H plus l, it is 3. E raised to power iota pi 3. Now what does it contribute? This is minus 1, this is minus 1, 0. Please check. You can take another example. 3, 2, 1. Again mixed, na? 2 are odd and 1 is even. So now what is h plus k? 5. H plus l. 4. K K plus L, 3. Now again, please check. This 3 pi, iota 3 pi will contribute to minus 1. 4 pi will contribute plus 1. Now again, you are having 2 plus 1, 2 minus 1, again it is 0. Please check everyone. Clear?
Yes, sir.
These are called selection rules for reflections. So now we can make a table of these selection rules. Okay. So kindly write the heading. This is very important. Selection rules for reflections. Structure. Allowed reflections. Simple cubic. All are allowed. Body centered cubic. Which reflections are allowed? Tell me. H plus K plus L. Face centered cubic. H, K, L are either all even or all odd or unmixed. You can write H, K, L unmixed. And you can note down for the diamond cubic also. Similarly, for diamond cubic, again, H, K, L are unmixed. Just similar to face centered, but there is one more condition. Now, unmixed means either all even or all odd. Or let me write in more. Either, because there is one more condition on even one. Are all odd, or if they are even, H, K, L are all even, then this sum should be divisible by 4. That's why I've written and. Means if all of them they are even, then their sum should be divisible by 4. Means this is the case of even. 0 is also a case of even. This one is not allowed in diamond cubic because sum is not divisible by 4. Okay. Similarly, this also 2 to 2 is not allowed. Although all of them they are even. But their sum is not divisible by 4. Please check. But this will be allowed in FCC because all of them they are even. That is the difference between FCC and diamond cubic. Please check. Okay. Clear?
Yes, sir.
Now, let me tell you again with the help of table. Okay, let me tell you again. Let us make a table with H square plus K square plus L square values, and then it is simple cubic, FCC, BCC, diamond cubic. Okay. Now, what is the lowest possible value of HKL? It may be 100, so it will become 1, H square plus K square plus L square, corresponding to 100. And 100 will be allowed in simple cubic. Is it allowed in FCC, BCC, or diamond cubic? No, no. Because sum is not even, so in BCC it is missing, and they are mixed 1, because 1 is odd and 0 is even. And what is the next possibility? H square plus K square plus L square equal to 2. So then it will be 110 or 101 or 011. Now the sum is even. So it will be allowed in BCC, but it will be absent in FCC and diamond cubic. Now can we get H square plus K square plus L square 3? Yes. If all of them they are 1. Now all of them they are odd. So it will be present both in FCC and diamond cubic, but it will be absent in BCC because the sum is not even. 4, 200. This will be allowed in FCC, but it will be absent in diamond cubic. It will also be present in BCC because the sum is even. So can we get 5? Yes. 210. So this is the mixed case now. So this one is not there, not there, not there, because sum is odd. Now 6 is there. Yes, 211. This is again mixed case, but this will be present over here because sum is even. We cannot get the sum 7 by any means. X square plus K square plus L square. Next possibility is 8. 222. This is present. This is present. Here it is not present because sum is 6, which is not divisible by 4. But 222 is no. It is 12. 220. Sorry, it should be 220. So it will be present. Is it clear up to this point? Please check. If you have any doubt, you can ask. Yes. For BCC, I am checking their sum, whether it is even or not. If it is even, then it is present. For FCC, I am checking whether all of them they are even or all of them they are odd. If they are so, then that is present, and if they are mixed, that is not present. In diamond cubic, either all odd, and if they are even, then their sum should be divisible by 4. That's what I am checking. Please check it yourself. And I have taken the planes in increasing order of this. Actually, I have taken the sum of squares of the Miller indices. So that is the difference between different crystal structures. So you can see in diamond cubic, we are able to get only 2 reflections up to 220. Whereas there are 4 reflections in BCC, 3 of them in FCC, and all of them they are present in simple cubic. 7. So there will be 7 peaks in simple cubic up to 220. There will be 3 peaks in FCC up to 220. There will be 4 peaks in BCC up to 220. And there will be only 2 peaks in diamond cubic. Is it clear or not?
Yes, sir.
Yes, sir.
So these things you are not going to get in the books. Okay. All of these they are self-made fundas. Very important for you. So no issue. Saturday also we will be discussing about this. When I will discuss some of the numerical problems, then the things will be more clear to you if they are not clear at this point of time. But you should revise all of these, okay? These structure factors and how they can give rise to a particular peak in the diffraction pattern. Okay. So that's all for today. Okay, students. Bye bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.